All right. Hello, everybody. Welcome. This is Open Research Institute's FPGA meetup for FPGA-based projects at Open Research Institute. Today's the 11th of March, and welcome to everyone. What we do at this meeting is we talk about what we have done over the past week, what we have planned to do over the next week, if we have any roadblocks that we're having trouble with technically, and if we need any resources from ORI. And so today we're going to talk about some FPGA work on Opulent Voice, and then we're going to move into a review with some significant review input for the Earth, Venus, Earth link budget that we were doing that involves multiple citizen science organizations and sites around the world. So we're trying to do our very best to provide really good quality work there. Okay, so let's start off with Opulent Voice. I think there's some pretty significant updates just over the past couple of days, and I see Paul's here. Would you like to go ahead and speak to those?
Yeah, I can do that. Matthew has mentioned on Slack that he's not going to be able to make it today, so it's up to me. Um, as you recall, we've been having trouble with the two Pluto situation where one Pluto is transmitting, the other is receiving. And we made some progress on that, I think. The first thing we did was uh, we'd already uh, used had both Plutos hooked up to the same external clock source, and that seemed to work. That more or less the way expected, but with some glitches. I hooked up a second uh, external clock source out of my own lab that we have borrowed from the local ham group, so I could start to manipulate the relative frequency of the two receivers. And with them dialed onto the same frequency, we got the same result as a single clock. So that's good. Um, that means there's nothing really weird in the dependency. It's just the frequency, as we had thought. Um, and we got off on some tangents. And one of the things that we've had from the very beginning is that the exact number of bits in each approximately 1 second test period has been varying in a weird periodical way. We sort of knew why, because we're trying to do precise timing under Linux and with a spin loop, and it's not really going to ever be very precise. But we have had in our back pocket a hardware-based timer provided by the hardware in the Pluto, not not a feature in the FPGA, but an actual honest to God hardware that's counting the CPU clock. And we now implemented that into the application code, so we can keep time much more precisely. Uh, and sure enough, that makes the periodic variation in the number of bits per period largely disappear. We now have a nice flat line where we used to have two that sort of interlocked and went up and down in a in an unexplained period. So that's good. Um, that cleans up the display on the graphs quite a bit. And the next thing that jumped out at us is that the exact right number of bits, plus or minus a few, because there's still uh, some timing slop, uh, is the most common value, but it's not the only value. Sometimes we see almost exactly twice that much, and very rarely we see almost exactly three times that much. And those are in sequence. So we get one too many, two too many, three too many. And what it really looked like was that when we reset the counter in the PRBS monitor to make another 1 second test interval, sometimes it didn't work. Sometimes the reset just plain didn't happen. And there's enough trace output in the code that we can see that the bit being toggled that's supposed to cause the reset is actually being toggled for that exact data point that is out of line. So somehow those um, those writes are not having their desired effect. So I showed all this data to Matthew, and asked him to go investigate how this sort of thing could possibly happen. And he's figured out that there's a problem with the clock domains that interface between the CPU clock domain and the clock domain that actually is doing the signal processing wasn't done correctly. And he is going to try to fix it. And when we get that fixed, we'll run some new tests, and hopefully the problem with resetting the the uh, the bit count will go away completely. And we hope that some other unexplained bizarre behavior will also go away because it might have been caused by register writes going astray that we are not able to see clearly. But whether or not we get that extra bonus of bizarre behavior disappearance is uh, yet to be determined. But at least we'll clear up the problem with the bit counts, and things will get clearer and get us closer to a working over the air demo.
Wow, thank you. Yeah, that's quite a lot. No, very appreciated and looking forward to the results over the probably over the next week, if not later today or tomorrow.
Depending on Matthew's availability, yes. It'll be easy to test once we have the new version.
Okay, wonderful. Yeah, we'll just keep an eye on GitHub Ops. That's our channel on Slack that lets us know when things have been updated for the repositories that we have, and then we'll build it and test it. So thank you very much. That's a very encouraging report. I have a report from Aaron Olivares, and he is a lead for OpenCPI, and that is a large open source project that is implementing Opulent Voice in the MSK work. And he's been a major contributor. He's on the road today during today's meeting time. We hope he drives safe. He won't make the call. What he worked on this past week was DVB S2 test environments. So digital video broadcasting, a satellite second edition. That's what we use for our downlink for our GEO and HEO spacecraft projects. He set up GNU Radio to run flow graphs to transmit and receive DVB S2 GSE as discussed last week. He looked at our history in GitHub and previous efforts and received most parts to build the Pico tuner, which is a follow-on to the tuner project from Everest's side of the project. He's still waiting on some parts. He has some reports on the PPS clock sync, hooked up the GPS PMOD module to generate a PPS signal, confirmed he's receiving it inside the FPGA. This is a big step forward. He says, I've been working on implementing a simple frequency counter to validate the clock frequency changes made by the DAC. It's moving forward. And what he anticipates to do over the next week is to continue working towards replicating DVB-S2 testing locally, as well as to progress towards clock sync for the AD9363. So the AD9363 is a very closely related chip to the AD9361. That's the chip that is on the Pluto, very commonly used chip, what we would really like to leverage. What he needs to get with Matthew to get a tutorial on how to do the MSK, or minimum shift key simulations for Opulent Voice. And he mentioned last week getting a summary on the DVB S2 testing and experiments made at ORI, which I promised him and I have not done yet. I apologize. It's on the list and I'm not sure where the week went, but it went. But I owe him sort of a context and an onboarding for that particular set of work. So thank you very much to Aaron, KI5BAB, and read out your updates to the meeting, and looking forward to getting you some more support, and look forward to the next time we get to meet. All right. Any other reports for Opulent Voice or any questions about that work? Okay, so another large portion of our time has been spent on an Venus-Earth link budget, and this is for an effort the very closely impending inferior conjunction for Venus is coming right up here in later in March on the 22nd, 23rd-ish. And this is an excellent opportunity to do some bounce. So this is a sort of a same idea as Earth, Moon, Earth, where you bounce off signals from the moon and receive them here on Earth. And there's a very active community and a lot of technological advancements and leveraging all sorts of different things to get that done. We're talking about doing this on another planetary body. The closest planetary body to Earth is Venus, and the Earth, Venus, Earth link budget, which came out of a request through Rick, who's on the call, from the Deep Space Exploration Society originally, is now expanded to include different groups. And what we'd like to do today is talk about the feedback that we've received. And Lee, WAAYBT, his feedback is represented here in these slides. And thank you very much for being here in person. So I'll defer to you at any point if you would like to correct or expand on the slides that reflect your feedback. Also, Thomas, thank you very much for joining us. He's from Dwingelo, and that is a major site with a very large dish involved in this effort. And then Pete Wyckoff, who has extensive experience in spread spectrum and RF engineering and information theory, and has contributed towards the success of this particular document. So I have a set of slides, and I've incorporated the feedback that I've received from many sources for today. And what I'd like to do is to start a review and to introduce the feedback. Some of the things that have been talked about in the slides have already been corrected or corrected to the best of our ability. But I'm including the feedback because it may help us to improve our corrections. But before I start, is there any other questions or any other concerns that anybody would like to bring up? Okay, let's go ahead. We'll go ahead and start. I'm going to attempt to share this. So what you should see is the EVE link budget comment and critique slide deck. And you should see the slides changing. Is that, everybody seeing that okay?
I see it.
Oh, thank you. Okay, good. All right, so yes, welcome. This is the 11th of March. This is a review of our link budget work. And you can find this document at this URL. This is our Open Research Institute GitHub project, and we have a number of repositories there. One of our biggest repositories is our documents folder. And in the documents folder, under engineering, under link budget, is this particular link budget work. So at this point, the successful review in anticipation of that, we will probably split this out into its own repository so that folks can find it a little more easily. The first set of feedback that I'm going to discuss is from Dr. Daniel Estevez, and he's a sort of a well-known person to us. We use the Maya SDR package that he developed on our Plutos as an instrument. And he's also helped frequently in the past, and we've interacted with him a bunch. So a known person. If you're not familiar with him, please go to destevez.net and see what he does. He has an amazing blog, highly recommended. So in the context here, we took out what is often called an adverse margin in our link budget until we could agree on where and how much, since it makes a very big difference to detection. And when we say we took out a margin, this is like, okay, after you've done all of this work with the link budget and you've gotten to the point where whether or not you detect it, how much extra margin do you need in order to say, yes, we have detected a signal? And Dr. Estevez's advice is that 0 dB, which was our provisional, like, let's just bust it back to 0 dB for now, is far from enough for detection. And yes, we agree, we know that. Since you need to look at many detection hypotheses, the chances that the hypotheses with larger detection metric is wrong are rather high at 0 dB. And as a ballpark, you're going to need 10 dB. Okay, so you need 10 dB extra in order to say that you're detecting an actual information-laden signal. This falls into the 10 to 13 dB range from the IEEE paper that Thomas requested and that we've used to help construct the link budget. And this is also echoed in feedback later on in the slides. So we're getting lots of confidence that yeah, we need to use 10 to 13 instead of 3 or 5 or 7 or just some other number that we picked out of the air. Um, Gary Lauterbach, K6MG, wrote in. He's from the San Bernardino Microwave Society and is an experienced RF engineer and a technologist. So he addresses a number of points in the one of the link budget revisions. We asked, what can we do? There's three things that we can look at about the non-coherent integrations. So we can add more integrations. And he said instead of 10 dB, you need to be using the 5 dB. So we did catch that. That's been corrected, but he pointed out that the comment was still inaccurate. So that's going to be fixed today. Now, he asks, why do you say that the coherent integration period is limited by changing the Doppler shift? So we do set up a situation in our link budget where we limit the coherent integration period for Zadov-Chu. We're just saying, okay, so we have a Doppler rate of change that is the highest when Venus is closest to us. So as Venus is going by us, the closest to us at inferior conjunction, we have the lowest raw Doppler rate, but we have the highest rate of change. So it says you're seeming to say that you're tracking it, but if you're tracking it, then you don't need to worry about the rate of change. So this does need to be clarified. This is also addressed by Lee. And it's because that we don't know if there's any closed loop tracking at all on any of these dishes. So we need to assume that the only thing that they can do is correct between sequences. So you correct the Doppler between sequences, and then you sit there and you receive for the however many seconds that you need. That's what we've assumed in the link budget. So this needs to be described and documented, I think, a lot more clearly since we're getting these questions. But to answer the question, we're doing an integration, a coherent integration where we're not doing anything except sitting there and listening long enough. And what we do is we design that integration period to be long enough to where the very high rate of change of Doppler during inferior conjunction, that's the highest, and that's what we're going to design for. It says, brings up an issue that I didn't really know a lot about. He says you've not considered temporal spread. And he says, he has a definition here. It's 40 milliseconds with a chip period of 2 times 10 to the negative 7th. You're going to need this many PN sequences to sum to collect all returned energy. Okay, so he's raising an issue that we don't have currently in the link budget about temporal spread. So we're going to have to look at that, learn, assess, weigh, consider. So if anybody has any sort of ideas about this and how to sort of derate our budget, that would be good to listen to. And then he goes on, says, given a 6,000, oh, go ahead and see, Pete, why don't you go ahead? If you have, can you talk about
Yeah,
this right
yeah.
now? That'd be really great instead of later.
The temporal spread is the thing we've been talking about with different chip rates. So if we pick a really high chip rate, then what happens is each individual crater and pebble on Venus returns in a different time lag of the matched filter. So in effect, then we have to derate the size of Venus to more like the size of pebbles and craters. And so what he's talking about here is if we have a way to sum those up, then we get all the energy. And one practical way to do that is just use a lower chip rate. But
Okay.
I mean, there's you could do it in receiver processing, but it's more processing that, I mean, you could go either way, but just a lower chip rate would get you all the returned energy, like you said.
Oh, okay, that makes sense. Is this sort of like a rake receiver?
Well, so there's two ways to do it. If you go at a high chip rate, then they're at different lags, and that would be like a rake receiver. It's in time and frequency in this case because you have so much resolution. But the other way to do it is if you send a lower chip rate signal, then it blurs the returns in delay. And you can get returns from basically the whole surface of Venus in one matched filter output. So that's collecting the returned energy. There might be one wrinkle in it that, if we integrate for, let's say, a second in the coherent matched filter, we have a hertz or so of resolution. And so some parts of Venus may have more than a hertz of Doppler. So you might end up with a rate across frequency rather than time that you're more familiar with from like IS-95.
Okay. Yeah, thank you. That really helps. Okay, so I think we have a little bit of work here to do, and we were already moving in this direction and starting to talk about the the rates. They have a big impact. So thank you. This now makes a lot more sense. Okay, so the second point here is it says given a 6,000 kilometer diameter for Venus, the return energy is spread over this 40 millisecond window. Talking about dual temporal spectral spreading. Okay, so I think this is more about this this related issue. Now, on the other hand, this provides astronomers the mechanism to do planetary surface mapping by pixelating the surface into the delayed Doppler regions. Okay, so that makes a lot more sense. Okay, so you also looked at the CNR and SNR calculations for the modes. So this is a mode evaluator section of the link budget where we go and we say what modes work. So given our 1 hertz CNR result, and when I first read this, I was like, oh, I think we already have handled this, but I want to make absolutely sure that we have. Um, so he's talking about the bandwidths used in the various modes, and he says they're not the coherent integration bandwidths of each mode, but the occupied spectrum for a full message. And he says, okay, if your goal is not to send and receive a full message, if we're not actually trying to do communication, but just getting a single bit back, that we're just saying that you're successful in EVE detection, is advising that maybe we can approach this particular section in a different way. And for sure, we need to be clear about what we're after here in this section. When we say that the mode doesn't work, if the mode doesn't work for communication versus the mode doesn't work for detecting a single bit in the entire message. I think that's what this is getting at. It says the coherent integration period for all of these JT modes is the symbol time, and the coherent bandwidth 1 over the symbol period. And if you use that, you can increase the knockdown effect is that you increase the impact of Doppler spreading. So something we've already talked about is that the narrower the bandwidth, the worse the effect from Doppler spread. And I just want to reiterate that Thomas corrected us in pointing out that the SNR numbers for JT modes are all given at 2500 hertz bandwidth. They're all already normalized to that, and they're not given at the listed signal bandwidths. So we switched to using these SNR numbers at the normalized bandwidths, and we stopped using what we might call the occupied bandwidth of the signal. So I, I think I understand what Gary's after here. He's like, okay, if your goal is just to get detection, like, is the signal there? Just need some indication that something's coming through rather than sort of the rubric or the bar of being able to send and receive a full message. Okay, so is this feedback something that needs to roll into the link budget? Do we need to change the way that we're doing the mode evaluation? No, go ahead, Pete.
So his point of just detection versus using the underlying mode is what I tried to make a spreadsheet that showed if we were integrating for 280 seconds, just chosen arbitrarily because it's the round trip time. So we could adjust that to these different modes and how long they're on the air. And then that would speak to the Eve detected.
Okay. So it sounds like it might be useful to maybe even have like to split the mode evaluation into 2 categories. Like, are you just using it in order to tell that you are there, or do you actually want to deliver the information?
Yeah, that seems really reasonable to me. Because like he pointed out, just detecting that there was an FT8 signal there is something you can do at a lower SNR than actually decoding an FT8 signal.
Yeah. And I think it probably would be good to bring up at this point. A lot of people that are probably watching this are going like, well, wait a minute, digital signals are designed to either be there or not. Like they don't have a graceful degradation like the old analog signals. So it might be good to talk about that, because there is a lot of talk out there, and a lot of introductory material saying digital signals are there until they're not. And it sounds like what we're talking about is a slope.
Well, and the detection versus demod and get the bits back was something that was covered pretty well when the FCC looked at cognitive radio, because they discovered that, signals you couldn't demod, you could tell they were present. And then that helped you avoid picking the channel for your
Okay.
cognitive transmission and disrupt other people's networks.
Okay, that sounds like a good reference or a good thing to leverage if we have to justify this in any way. Which I vote for yeah, we should take every opportunity to explain what we're doing. That's complicated stuff.
Well, it gives a chance for success too, because like on the moon bounce stuff from Dwinlow, we see about 8.5 dB of fading just on a CW tone. And so just depending on our luck, when we actually do this, it might be that we get one of the channels that doesn't permit copy of the message, but still detection as a piece of success.
Yeah, that's true. That's a good point. All right, thank you. That helps a lot. All right, and then Gary said mention was made of OTFS, which is a modulation scheme, possibly being a method to address the delay Doppler spreading, and he thinks that this is a very likely possibility, and says this reflection can be viewed as a highly multi-path environment, but with the reflection paths that can be pre-calculated, like you can predict them. He says no need for dynamic channel characterization. I'd say less need for that. Um, You also, so in addition, a bit error rate curves all make the assumption that the signal is present and then show the probability of a flipped bit. The model that's generally used is Gaussian noise with a zero mean and the 0 or 1 decision threshold placed at 0. So when you want to be sure that a signal is present, you're going to need to examine the statistics of the bit stream with no signal present. And with no signal, you get a 50-50 probability of a bit being in the expected state. I said we see this in Opulent Voice lab work all the time. The question is then how many bits are required to reduce the false positive probability to a desired value. So this is him addressing the discussion about, like, okay, that 0 dB threshold, why you need margin, why, just in case we needed convincing that we we need margin. And this is a very good I thought this was a very good discussion. So he has a recommendation for a lecture on YouTube, and this is from MIT. It says, okay, if you take this probability of a false detect and 10 to the -6 probability of a false detect, sort of equivalent to your acceptable bit error rate in information theory, then you have a bit stream with a 50-50 bit probability would need to be 20 bit long to achieve that 1 in a million false positive rate. So when you do that, you take this 10 log 20, you end up with 13 dB, which is the energy increase required to reduce the false positive error rate to an acceptable level. So he says, pick your probability of false positives and false negatives, and the SNR will drop out of that. And this is actually a good information theory result. And I think it's probably why the IEEE paper that we've been using says 10 to 13 dB. So we have two very different people reinforcing the same idea from two different directions. Um, and I was already comfortable with like having a margin, just wanted to know a number and why. I think we're getting a lot of good information on that. Geary has been studying the area of delay Doppler spreading in planetary radar for 3 years. He wants to find a scheme to enable coherent integration in the presence of spreading, and the application he's most interested in is millimeter wave Earth-Moon-Earth communications. And he says in this case, the spreading is far worse than what we've kind of been talking about. And I'm hoping that we can support his work and help him out here, or at least just give some positive vibes. This sounds great. Sounds like a really cool thing to do, and I was very excited to be able to talk with him more. I know him through SBMS, and really appreciate the feedback and the kindness and generosity and sharing his experience with us. So, what is delayed Doppler spreading? I thought this might be a good thing to talk about. here today. And the very basics. Uh, if you're an RF engineer or interested in radio, um, you're going to know that things happen in the time domain, and then they happen in the frequency domain. And we switch back and forth between these all the time, and it's magic. It's really wonderful. Fourier transforms are great. The first time that you get it, that your time domain can be turned into the frequency domain, and you basically get to leverage your problem into a different way of thinking, and it either becomes easier or much harder, is great. Okay, so we're good. The time domain is a delay spread. So time domain is has delay. The frequency domain has a Doppler spread. See, so we're already good. The delay Doppler spread, you already got a good traction on this if you're into radio and know about time series and frequency domain. The delay Doppler domain gets both of these effects and puts them together and tries to make a framework, a compact framework for us. Now, it does take you got to take a deep breath and wrap your mind around it. But wireless channel, your signals can be affected by both of these. You get different signal paths arriving at different times due to reflections. That's the delay spread. You get frequency shifts because there's relative movement between a transmitter, receiver, and reflectors. Okay, so in a lot of cases, as RF designers or as RF engineers, we have to deal with delay spread, like the multipath thing. If you have a fixed network, you figure out your different signal paths and you have techniques to deal with that. If you have stuff moving around, though, you're going to get Doppler spread. And for the thing that we're talking about for EVE, we've got both. So, we should pay close attention here and see what it can give us. So what's the value of looking at things with respect to a delay Doppler channel? There's big advantages. The time frequency channels might be ugly looking, smeared and weird. And the delay Doppler representations can be really concentrated and give you a structure. And I think we've started to see that with some of the images that we've seen, from Thomas and others. So when you look at this side of radio frequency engineering, you can start to see that, yeah, these representations really kind of communicate a lot to you. You can get it rather than having to look at a time frequency channel and you're like, it may look like a mess because of these effects. It's stable. So when you have a channel representation in delay Doppler, even if you have a lot of stuff moving around or at high speeds, it's a little easier to track it. So we know that once we can measure something, we can control it. Like if you can't measure it, you can't manage it, right? So looking at it in these channels, in this channel representation is advantageous for us. So it's a good model to consider using. And it's separable. You can handle the delay and the Doppler. You can separate them out. And that means that you can have equalization. And we all know that equalization is super useful. Okay, so we've talked about OTFS modulation briefly. For a lot of us, including myself, very new concept, not really dealt with it a lot. Gary was very enthusiastic. He thinks that this is a good thing to look at. OTFS modulation, which is a delay Doppler, it's like OFDM, but OFDM has time frequency. OTFS has delay Doppler. So same sort of resource grid and the way that the information is spread out. It uses a delay Doppler grid instead of the time frequency. And it allows you to spread the data symbol over the entire time frequency grid, making it very resilient to localized fading. That's a good thing. You're going to transform your traditional time frequency into delay Doppler, and then you structure your channel. And you can convert these into what's called quasi-static channels in the delay Doppler domain, which just is reinforcing the idea that things look better. If you have this high Doppler, high delay environment, things moving very quickly, zipping by, this is just a way to give you more traction on it. Okay, so analogies help me a lot. I'm going to try very hard to give you a good one. If you can imagine OFDM, orthogonal frequency division multiplexing, as trying to have a conversation in a large, big room, like a cathedral, and your words are bouncing around. They're all arriving at different times. Sometimes these big cathedrals have multiple seconds of delay. It's amazing. Okay, and you're also walking around while talking, so you're going to be walking around really fast, causing Doppler shifts. So OTFS is like having that same conversation, but you have special glasses that let you see exactly where and how your voice is bouncing, and you have a microphone right there that can precisely focus on just those specific reflection points. And you can turn this complex environment into a structured and manageable one. And that's kind of what we're talking about doing when we talk about delay Doppler transceivers, receivers. So those special glasses, you can get that by using things like Zadov-Chu. These are those reference signals that we've been talking about, and they let you estimate the delay Doppler channel. You can also use some other things. You can use two-dimensional symplectic Fourier transforms. And I say UG because having dealt with these at least once in the past, I found it a little tough going, but they're mathematical operations that convert the time frequency to delay Doppler. So once you get it coded and tested, then it just works for you. That's great. You can use match filtering, and you can use channel estimation algorithms like you do with OFDM. And you can extract the delay Doppler channel profile. This is kind of the hard way because it's just constantly measuring, constantly doing it all the time. And then you can do like a delay Doppler channel sounder. So instead of relying on a pilot tone, you can actually say, okay, this is actually overlaps with the pilot tone, but you can do a channel sounder. You can set up some sort of beacon separate from your communication channel and get those things. None of these really work for us because we don't really have the ability, or none of them except for the first one. We can use Zadov-Chu reference signals, and that can give us the information. The rest of them, some of them rely on like third party or separate things, or so the first one is probably the best. This special microphones that we're talking about, this is signal processing that's done in the receiver, and you're doing equalization. So these are mathematical operations. What you're doing is inverting the channel effects or reversing the channel effects based on what you're estimating the delay Doppler profile to be. And you can do this also with what's called an ISFFT, inverse symplectic fast Fourier transform. You can do this in hardware or any circuit really that can detect and process signals, and delay Doppler can help here. Lee, he gave us some really good feedback, and he's here today. So I'm going to go through these slides, but I'm going to defer to Lee. So if you want to raise your hand or take over, then I'm just going to go through your points. So at any point, please correct me. He wanted to point out that the tracking error probably only need to be concerned with the open loop pointing error, not tracking error, since we're generally not doing closed loop tracking. And so I tried to represent that in the link budget, but it raises a really good point. And then tracking error is generally SNR dependent and also depends on the tracker design. And there's a lot that we don't know about the different trackers at different sites. So I think less is more when it comes to the link budget. Having a good representation of like pointing error might be a really good idea, so that when we get a pointing error estimate from a site, that we know how much to take out. He talks about the Venus radar cross-section, and the radar cross-section is defined as you have the projected Venus cross-sectional area, and you multiply that by the albedo, by the backscatter coefficient. So I think that's where we are today, that we're correctly doing this. And I'll go back and look because we started out trying to include what's called like the billboard model to say, okay, imagine if Venus was a flat billboard and reflector, and what size billboard would it be? And that turned out to be messier than just saying, here's your cross-section, radar cross-section times the albedo. You reduce your physical cross-sectional area by the backscatter coefficient to get an effective area called the radar cross-section. So I think that's what we did. We should double check. He says remember, these are spherical reflectors and not flat billboards. And he has a equation for the radar cross-section of a flat plate here. just to say, okay, here's the RCS. He talks about the billboard gain. So we did have billboard gain in there. It's been modified. And again, what we'll do is make sure that that we've done it right. And I think, and somewhere in here, I think he also says that the albedo definitely includes the atmospheric loss, which is because we had that as a separate term from DSES and have since dropped it, or it's still in the data class, but is no longer as part of the loss. It talks about pointing loss, and you can approximate it with this equation, and says it's a good parabolic model for the main lobe shape. So that will be taken into consideration and used. Talks about libration. Should have no effect on the cross-sectional area of Venus. I agree. We get libration effects with EME, but it's not going to be something that we have to worry about in the link budget for Venus. And then here's the point about Venus atmospheric loss, which was in the link budget and was part of the loss calculations. We did correct that. But the albedo should already include the effect of the two-way Venus atmospheric loss. So I think we got that covered. Earth weather effects, we do have that in the model. We have a simplistic model for Earth weather effects, and he has some additional feedback here. And says we probably won't be operating in rain that's really heavier than moderate. And then clouds and fog have no effect on L band, so we don't need to worry about that, or S band, the 2.45. So we'll be working at 1296, and then at the next opportunity, we expect to be able to work at 2304 or 2.3 gigahertz. Main beam efficiency, I believe that this might be in the system temperature section. But he has some advice here for main beam efficiency is the ratio of the power received through the main lobe to the total power received through the full antenna pattern. Let's see. So yeah, main beam efficiency is infrequently used since it's difficult to calculate. So we need to look a little more closely at this calculation to make sure that we're not pulling off the value that we end up with. Yeah, more interested in the antenna gain. Okay, so I found this to be valuable and worthwhile to weigh and consider, and we may need to modify what we're doing. And so anyone here that has opinions about that, please help us figure out how the calculation should be published. It says aperture efficiency depends on the aperture illumination function, reflector surface losses, which I think we talked about that, and we still have that in the documentation and spillover. And this is definitely relevant since it reduces the antenna gain. And a lot of these numbers that are in like the system temperature portion, they really do have a huge effect. So getting it in the ballpark is really important, and then making sure that it's accurate. Any review here is going to be super helpful. So here's the main action items. Yes, we're going to be updating what we might want to call the adverse margin. So this is once you get back up to 0 dB that you're not there yet, that's almost like you build a Linux system and you get a, there you go, you get your prompt, right? Well, that's not the end of making a functional system that you can use. A blinking cursor is only the beginning of your adventure to getting most out of your machine. So once you kind of get to 0 dB, you need to actually have enough margin in order to ensure communications, that's what you're after. And then if you're just after detection, then that's a lower bar, but it's still not at 0. So these things need to be updated and communicated. We need to adjust the mode evaluator with respect to SNR and bandwidths, question mark, with the feedback that we've received. And we need to revise the beam width and antenna efficiency numbers or policies on that. Like, we've got a set of calculations. And and those need to be a little more attention to that, make sure that we're doing it right. So a lot of the items pointed out have been fixed, but we need a careful review for all this feedback, which is going to happen today here at this meeting, the rest of the day, and tomorrow, in efforts to kind of get a version that we can be proud of publishing that we think is mostly good, and so that over the next day. All right, that's what I've got. So the floor is open for any corrections here or expansions, explanations, anything that I got wrong, anything that we have wrong, anything that we need to pay attention to more. So you all have the floor. Also, if you want me to go back to any particular point.
I've got a simple definition question that may be obvious to everybody else.
Go ahead.
Okay. Um, the the definition of a billboard, um, is that a shiny billboard or a matte billboard? And is it pointed in exactly the right orientation to make a perfect reflection, or is it in some other orientation?
No. Hi. Hello.
Oh, please go ahead, Lee.
Uh, oh, okay. I didn't know if you could hear me.
We hear
This
you.
is Lee, WAYBT. I'm a radar engineer. Um, I think we should stop using the term billboard reflector at all, because Venus is a sphere, and flat plates have very different reflection characteristics than spheres. So just a flat plate reflector is not applicable at all in this case. So I'd kind of like to purge that nomenclature.
Yeah, I'm completely amenable to that. The where this came from was it was some EME link budgets and some advice that we got. I was like, oh, just use this. It's just like a sphere is too difficult to model, so we're going to pretend that it's a flat plate that's facing you. To answer Paul's question, it's one that's orthogonal to you, like it's a perfect reflector. And then for the EME folks, they derate this. So it's not the width of the moon, it's a fraction of the moon. So if you can imagine the moon being turned into a disco ball and then fewer and fewer little mirrors, you get down to a point where, okay, the thing, the mirror that's facing you on the disco ball, that's really what's the dominant signal back to you. And it works for them. And I have some numbers, and I was like, okay, is that what we do for Venus? Um, and it sounds like no, and it sounds like also that you could actually improve the EME link budgets by using more from radar. Like, okay, it's really a sphere, and you will get some back. And I think Pete also had some really good visualizations of this, like looking at a sphere and looking at he was looking at it for Doppler spread, really, the rotation of Venus introduces some Doppler spread, but we're getting a fuller picture, a more accurate picture. So that's where it came from. So we just wanted to, like, okay, if that's what people are using in the community, then maybe we should put it in our link budget to start out. But it was really optimistic. These are like big numbers that we get back when we use a big flat reflector, which makes sense. Um,
Oh yeah, yeah.
so
But
yeah, I think we've
unrealistic.
adjusted it. But it sounds like I'm going to take what you've written and go back to the code and make absolutely sure that we have something that reflects what your experience and expertise is telling us. Oh, go ahead, Pete.
Yeah, in the radar equations, they always assume the target is a sphere, and that's the definition of radar cross section. It's the cross sectional area of a sphere. So that's kind of the standard in the radar world. And of course, a a, a bigger sphere reflects more energy. Uh, but it also reflects isotropically. So a large sphere reflects more back toward the radar, but it also scatters power in other directions.
Yeah, very good. Yeah. Anything else, Lee? Did I get it all?
Yeah, I think you summed it up pretty well. On the main beam efficiency, I think that applies more to the background noise or background noise temperature, whereas the aperture efficiency applies to the signal budget.
Okay, that makes sense to me. I think that'll be good to put in. Yeah, we'll try to get this as accurate as we can so that and another challenge that we have is multiple sites want to use the budget. And so I think if we define the terms carefully, because that's been my challenge in the past with using link budgets, especially like complicated ones that I get given to me, is and while I'm familiar with the vast majority of the terms, there's some that are not really well defined. Like margin will be stuck in somewhere, and the person that designed it might know what they mean by margin, but I certainly don't. And well, I don't know, 3dB sounds great to me, and then everything is wrecked. So we don't want to do that. We would like everything to be as well explained as possible and to give it some flexibility. This is almost an impossible job. No link budget is ever finished at none of them are, just like with any model, they're all wrong and some are useful, so that's the sort of the the conundrum that we have in doing this work. But we also want this to be a really good learning experience for people so that they can read along and like learn what all this stuff is, and if they want to break it out or to look at the documentation that they can see, what we were after. So having, I think the Jupyter Lab notebook approach is good because then you can have alternate cells and you can say, okay, this cell is for if you just want detection. This is if you actually want communication. So those are two very different categories of detection. And so I think we'll work really hard to make it understandable that way and defined that way. So I really appreciate your attention and all of the amazing feedback. It's really invaluable. They're very appreciative to you and to everybody else. Oh, go ahead, Pete.
Just kind of two quick points. One was the original data that we used for the strength of the return from Venus was Dr. Evans' paper, and he used CW and a 500 hertz receiver bandwidth. So we just want to keep in mind he was collecting non-coherently energy from the entire surface. And if we design a high time bandwidth, say off Chew or other sequence, then we're not doing that in each bin. So you just want to be aware of that in the budget. And the second thing was just a practical point. If we decide to go for the 10 dB goal, quick calculation looked like we need to send about 26 of the 280-second transmissions. And so, while that's possible in the numbers, my question is on gain stability over that amount of time. I mean, 26, we're talking several hours. And so like when I get the data out of Dwinlow, it looks like there's an automatic gain control perhaps in the receiver. And, electronics fluctuate in gain and things like that, as well as background levels that might affect AGC over time. So I guess I just kind of wonder about what we know about how stable the gain is over a couple of hours and 20 some odd different bursts that we're getting back, and wondering if we can non-coherently combine those and not have just one or two of them dominate the whole set, because it looks like in the output data we get IQ samples, but we don't necessarily know what the receiver gain was set to, is my only point.
Oh, that's a really good point. Okay, I think we should probably,
Can
at
I,
the
can
very
I,
least, we should write it down.
can I say two words about that?
Of course. Yes, please.
So yeah, Peter, excellent point, of course. This is, in any case, in radio astronomy, a big issue when you have long integration times to keep your gain stable. We certainly don't. So if you saw stable gain, that was pure luck. What we do is that we have a noise source with an extremely weak amount of noise. So you can actually mix it in your actual measurement. And that allows you to stabilize the gain in post-processing. But we will not have that up and running by the time we do this Venus thing. So unfortunately, we cannot use that. Maybe lowering the margin is the only solution we have left.
Well, Thomas, it sounds like it might be ready for the next time.
Oh, certainly.
Yeah,
Yes.
and I just wanted to put the idea out there. I know that we're trying really hard to finish, as good a link budget as we can offer the community before later in March. Like now we're talking maybe only 10 days from now for the inferior conjunction, but there's another one in 500 and some 80 some odd days after that, and we're in it for the long haul. So we would like to continue working on this and making not just a better and better link budget, but we would also like to help with any sort of custom modes or communications modes or any sort of support. So just I wanted to put it out there that we're in it for the long haul. So any sort of, let's say like a sort of a probe, that you would have a noise source that you could use to then normalize the signal to to take out the uncertainty. It sounds like that's what you're talking about, and that surely that might be ready in 500 days from now.
Yeah, it is. And you're absolutely right about the long-term focus. It's just that I'm a little stressed in getting a few things ready for 2 weeks from now. So my
Yes.
focus is a
Yeah.
bit different. But you're
No,
absolutely
yeah, thank
right.
you for being here. I know that the time is short, and both the SES and Dwingaloo and the others are very focused towards the near term and achieving all that they can. Really looking forward to that, and really appreciate your time spent on this particular thing. So hoping that the Zadov Chew and some of the information about how close the modes get can help. And then with the advice that we've heard today, some of those modes, the standard amateur modes, may actually be detectable. I think we've been looking at it, assuming that we would like communications. So maybe just can you detect a signal as there is good enough? And I think, we know from Bockham that that's possible, looking at their results from several years ago. So I hope that it helps.
Yep. Thank you.
Sure thing. Oh, go ahead, Rick.
I just wanted to mention that DSES has already begun design work, or not work so much, but design planning for the next attempt after this one, which almost inevitably will be at 2400 megahertz. Just something to consider. We're trying to figure out how to get full power at that frequency. It's much more difficult, simply not technologically, but just because we can't go buy it so easily. But yeah, our team is very excited about the work we're doing now and everything we're learning. But they're just as excited about whatever happens now. We're going to do it again next time, and we're going to be even better prepared next time with everything we learn now. So that means this link budget you're working on is critically important, in my opinion.
Well, we will absolutely keep working on it and keep bringing it up and keep giving it to you. Another thing that we heard from the community is a question about Mars, and it's this EME, but the M is really Mars and not the moon, because Mars is going to be close to us. And has anybody at DSES considered a Mars bounce?
It has been discussed, and it's particularly difficult for a whole lot of different reasons than Venus. totally different reasons. However, another project has been discussed, which does not involve high power, but it does involve some tricky planning and link budgets. And that is, we would like to duplicate what has been done in Europe. And that is, we would like to detect the signals from the not from the original satellites that are out there in deep space right now. And it has been done with dishes not that different than ours. Well, the problem is that that's at 8 gigahertz, and we've not done 8 gigahertz on our dish, but that doesn't mean a thing. We just go build it. It's receive only, and I think that's a pretty exciting project as well.
Cool. Okay, that sounds neat.
Also, whatever happens in the next few weeks, I will be taking whatever information we gather from that to the dish that's in the background behind me. I will be at that dish teaching a course in precision time and frequency for VLBI systems at Haystack Observatory, and I'm trying to get the MIT contingent there interested in DSES. The director of the entire site, not just the dish, but the entire site, is a friend of mine. We went to college together. So I'm hoping to get him to give me maybe some grad students or something to help us out. Because we have a lot of things we want to do at DSES.
Cool. Well, look forward to hearing more. And I think it's wonderful news, and best of luck with the networking and communications and your teaching at Haystack. That I know that's something that you've been involved with for quite a while, and it's really
More
nice.
decades than I want to admit.
been a while, and I'm really
was
happy that you're back teaching there. So that's good.
Originally, Dr. Tom Clark took me there, and eventually I replaced him. And that took a long time.
Very good. All right. Any comments or questions or redirections or any sort of action items, anything that we need to know about before we go? Okay, well, thank you, everybody. Like a special thank you to Open Research Institute for enabling all of this. Very special thank you to Thomas and Lee and Pete for the excellent feedback, and also to Gary. Thank you very, very much for all of the feedback. We could not do this sort of work and make it as the quality, high quality that we want without this sort of feedback and engagement and critique. So we're very, very appreciative. Special thank you to IEEE, especially the San Diego section. Gotten a lot of support there, and we have been in close touch with AES Society, Information Theory Society, and Computer Technology Societies. They're all very interested in this work, and I think there will be a lot of opportunity for support learning moving forward from those societies of IEEE. All right, so we will continue on Slack. It's on our general channel to discuss EVE link budget work, and we will continue to revise, update, put it out there, keep running it, testing it, and then we anticipate to go ahead and make a release. Like this is version 1 of the link budget. Fairly, like I said, they're never really done because they're a model of reality, and models are always wrong. Some are useful, that sort of deal. So we understand that it's just our best effort of trying to produce prediction of, will these particular modes work? What kind of modes would you like to have? What's your receive sensitivity? Those sorts of answers or guesses, estimates are what's in this document. So that's how it should be used. But we want to make a released version this next week. And so that's our goal. All right. So Pete, go ahead. Did you have a?
Nope, didn't have anything.
Okay. Very good. So yeah, everybody see you on Slack, and we'll meet back again next week with a report, with more to say, I'm sure. And then I think Rick, if you'd like to take what we've done today and represent it tomorrow at the DSES Eve review, that'd be totally awesome with us. I can give you a cut of the PDF before tomorrow morning.
That would be good. You're not going to be there tomorrow?
Unfortunately, no. I've got a pretty awful conflicts on Wednesdays these days. But I'll make sure that you have a PDF of our work so that you can talk about it at that meeting. I think Thomas is sometimes a attendee there, and Matthew as well. So there should be some people to speak to the estimates and what we've learned. So what I'll do is my very best to synthesize and properly represent the contributions of everybody that's given us invaluable feedback over the past week, and make sure that that's represented in the PDF and get it to you.
Okay, sounds good.
Okay, very good. Well, thank you, everybody, and we'll see you next week, if not on Slack.
Thank you. Bye-bye.
You bet.